Windows, and I must say I found this to be very interesting stuff. It helped me understand a lot more about why Windows is the way it is, because Windows is very strange, and that's what this class and the malware analysis class really, especially the malware analysis class, is all about how Windows works, and therefore why there are 100 ways to hack Windows. And so we're going to talk about these concepts, which are the way the Windows operating system works. We'll get there as we go ahead. All right, so the first thing is Win32. You've got an application programming interface. You cannot directly refer to the kernel in Windows 32 any more than you can in Linux. In Linux, you have to do everything through syscalls. In Windows, you have to do everything through their API. So they give you these libraries, and the libraries have entry points with certain functions. So if you want to open a window or make a TCP connection or do anything, you have to use the Windows routine that does that, and you're stuck with it. So that's the game here. That's the application programming interface, which we're used to. Everybody has them now. Facebook has one, Twitter has one. They have a certain series of methods you can run that will do something on their platform, and you're limited to whatever they want to let you do. This is all done with DLLs and dynamic linking, so most of the time the API DLLs are already loaded in memory because they're connected to other programs, and you're just going to connect to them in RAM and use the images that are up there in RAM. So here's what you have to call if you want to create a window. You call this function called createWindowEx, and then you have parameters here that are things like the title of your window and things like whether it has scroll bars and how big it is and so on. And there's just documentation on TechNet for these things, and that's all you can do is use these APIs. Notice the EX at the end, we'll talk more about that. There's a Microsoft notation, which is good to know because it makes it easy to spot these when you just run the strings of an executable. So the DLLs, as we talked about before, these are dynamic link libraries. They load into RAM. You'll have one copy of a DLL, and every program uses the same copy of the DLL in RAM. And you can see them in Process Explorer, which you've used in the project. If you look at that SDC host.exe, here's a list of all the DLLs it uses, and it uses an awful lot of them. And here's the description of the individual DLLs, and each one of those DLLs exports dozens of functions which you can use. So this is the portable executable file. EXEs and DLLs are both portable executables, just the thing you've been looking at with PEID and so on. All right. You can see them with PE View, among other things. So here's Notepad. This is one version of the Server 2008 version of Notepad. There are quite a few different versions of Notepad. But this one has an import directory table, so you can see the imports. Imports are functions it calls somewhere else. It's importing these, like the include statement at the top of a C file. So it's using this user32.dll, GDI32.dll, kernel32.dll, advanced API.dll, and so on, all used by Notepad, which is about as rudimentary a program as you can get. So here's common sections in a PE file. PE files can have many sections, but they always have to have a text section. Those are the instructions and data, and then they may have other kinds of data, iData for import descriptors, resources, and relocation data, about which we'll talk about more later. Relocation data is used for portable executables when you make them so they can position independent executables. They can be relocated in memory. That's the plan. So DLLs have a base address. Remember, programs all think they are loaded at the same virtual address. They all think they're loaded at 400,000 in hex. DLLs have a certain place they would like to be, and they will load most efficiently in that location, but in case two DLLs try to load at the same address, that's not permitted, so they get relocated. That's called rebasing, and that uses the relocation section to indirectly jump for every method so it can be loaded in its non-optimal position. So I got a few eye-clickers about that stuff, and then there's more to come. Get this thing running. Yes, there we go. All right. Come on. All right. So, what kind of files contain precompiled library code? All right, I'll wait till 35. See how many participants there are. All right, those are the DLLs, dynamic link libraries. Okay. API is not a type of file. It's a function, but it's not a file. All right. So what term describes the set of functions Microsoft provides for you to access the kernel? I guess I'll quit at 30. All right, that's the API, the application programming interface. And it's not always kernel functions that you're getting to, but that's one thing you can get through to the API. All right. What's the overall format for all Windows executables? All right. Looks like I can quit at 25. All right, that's portable executable. Good. All right. And which section is used for rebasing? All right, I'll quit at 20. Looks like 20 is enough. All right, that's the relocation section. Good, all right. Which section contains machine code instructions to be executed? Guess I can quit at 25. That's text. Strange title for it, in my opinion, but that's the way it is. All right, where are the icons? I'll quit at 25. All right, those are in the resource section. All right. And if you get a program called Resource Hacker, it's intended to let you mess around with programs and games to change the way it looks. It can be used for other things, but it's one of the script kiddie kind of tools to let you play with Windows executables. So imports are functions that your program is going to use that are somewhere else, typically in a DIL, and exports are if your program is offering to do a service for some other program. So most of the programs that a developer will write in EXE do not have exports, except one, just main, to enter at the main point. The only thing that has a lot of exports is typically a DIL, a library, which might have dozens of functions, and then you have dozens of exports, which are ways to enter the program. So here's the imports for Notepad. This is the Windows 10 version, so it looks a little different than the last one we looked at. And the imports are actually in a different section here. Instead of being in a, I thought this was kind of interesting. If you look at the previous one, this one here, the imports were in the bound import directory table up here in the NT headers, but the later version of Notepad put them in a section iData. So there's different ways to do the same thing. But anyway, here's the same result. It's using a lot of DILs. This layout shows you advanced API32.dll, and it shows you exactly which functions it's using, like get token information and register set value and register query value. So if you want to write something to the registry and read what's there and only write it if it has to change or something like that, you'd have to use several of these API calls to do that. Yeah?
So if a program is an import table, which means it's specifying what libraries it wants to load.
Yeah.
How does that information get into the executable when you compile it? Like
It does not get in there at compile time. It happens at runtime.
Okay.
That's how the dynamic link libraries. You compile it, and when it runs, it then connects to the DLLs that are in memory.
Right, but it had to say what DLLs, it had to compile the executable with the list of DLLs.
Yes, it does. That's right.
So when you write a program, you only include headers to use other libraries. You don't say, like, what part of the compilation process automatically puts that library name in the
It's a good question, and I don't know the answer.
Okay.
But I do know that this will only have the functions you really use, not every function in the library.
Okay.
So I think that's what the compiling does,
Okay.
is prepare this portable executable with the right things in the header, and then the loader, when you run it, connects it to what's out there.
Okay.
Yeah. All right. Good. All right. So here's a DIL file, and here's all its exports. And so this one DIL, Advanced API, has many, many exports. In fact, this is still the A's. So a lot of functions come out of this one library, and that's the Advanced API that will just do an awful lot of things, like check accessing things and abort system shutdown and many, many things. So that is the Windows API. And as you know from glorious Windows 98 and every other Microsoft operating system, you frequently get these messages that the DIL you need cannot be found, and it can break your heart. I remember Windows 98 trying to dig through those cabinet files to find the stinking DIL, and sometimes I get so frustrated I just Google and go to these horrible, goofy adware sites and download some DIL, which is all pirate software because it's all technically Microsoft, and it's very frustrating. This is because fundamentally, Microsoft never learned this concept of the link counter. See, in Linux, if you use a file and then another program uses the file, it increments something called the link counter. And when another program uses it, increments it again. And when you uninstall programs, it decrements it so it knows when you're no longer using the file, and then it deletes it. But Windows, as you may remember, when you uninstall a program, it says, this program is using the following 6 DILs, random gibberish. Shall I delete them or not? And I'm like, you're asking me? How am I supposed to know whether I should delete them or not? But anyway, the uninstallers randomly make decisions whether to delete that DIL without knowing whether some other program is using the DIL, and you end up in DIL hell, where stuff you've installed suddenly quits working because DILs have vanished. By the way, I should mention, we learned something awful in the lab. In my mobile device hacking class, we're trying to jailbreak iPhones, and we had to install this thing that lets the TCP port point out the USB port. And it's a executable and a DIL in a zip file, which you put in there. And if you take the latest, the version of Windows 10 in the lab, which is about 2 months out of date, and you put those two in C Windows System 32 and run it, it tells you, I can't find the DIL. And if you open like Notepad and look for the DIL, it's not there. There's a bug in Windows Explorer, and I've seen many similar bugs, where it doesn't really show all the files. And the operating system can't find a file that is totally right there. It's I've seen this happen before. Another thing that used to happen a lot with XP and I think Windows 7 in the earlier versions is I'd have a file on the desktop, I'd rename that file to another name, and now there would be 2 files on the desktop with both names for like 5 minutes. There are a lot of weird bugs in Microsoft's Explorer, and in Windows 10 they come and go. The updates keep breaking something and putting it back until you think you're going mad. Anyway, Stuxnet exploited this. There is a trick, a really disturbing thing about DILs, especially in older versions of Windows, like Windows XP. So suppose you run an executable, and then it wants to load a DIL. The first thing it looks at is the current working directory for the DIL. So this is how we trashed the Iranian nuclear isotope separators. We had a DIL file on a thumb drive. When you plug in the thumb drive, the operating system tries to run a process within Explorer that shows you the contents of the thumb drive, and it needs a DIL, and it loaded this DIL from this location instead of from the real system location, and that DIL was the exploit. So it's easy to trick Microsoft Windows into loading the wrong DIL file and running malware, and that is the most popular way malware executes, is by just adding a library at runtime full of malware into your otherwise good code. So I mentioned everything is at a relative virtual address. Every program thinks it's running at the same address, 400,000 in hex. And so that's what it refers to everything as. The operating system, it's like a virtual machine. Every program is like a little virtual machine thinking it's using address 400,000, when in fact it's somewhere else, wherever the operating system put it, but the internal workings of the program think it's running from this relative virtual address. All right. And this is the relative virtual address, which is used to aid in rebasing DILs. And here's an example of this explaining how a physical memory address visible by the CPU. So process A is at 300,000 and process B is at 500,000, although it's hexadecimal, so it looks like 500,000, but it's really powers of 16 instead of powers of 10. But they have a mapping table, so they both think they're running at 400,000. Their internal addresses are all the same. That's the way it works. And OllyDbg, if you load any program in OllyDbg, you will see that it's starting at 400,000. This gives you the relative virtual address of this program, not the absolute location in memory. All right, so then there are heaps. As we know, the heap is used for temporary storage of data. When you have something you don't know how big it's going to be, you allocate space while it's running with malloc, and then when you're done, you free it, and you can use that space again. The Linux has one heap, but Windows has many heaps. Each DIL can set up its own heap, so heap corruption attacks in Windows can get very confusing. And then there's threading. There's a fundamental problem in all computing, which is that you have fast components and slow components. The processor is super fast. RAM is hundreds of times slower, and there are things that are thousands of times slower, like the hard drive and the network card and the ridiculously slow human tapping keys and moving the mouse. So the last thing you want is for the processor to be waiting for something slow to happen and getting nothing done. So each process, which is a program you might launch, for example, and then is written to break up into threads. So it has independent parts of the program that can proceed without depending on another part, so that while this thread is waiting for something slow, the other thread can go ahead. And processor time is actually allocated to threads, so each thread gets a chance to move forward. This tries to get as much efficient value out of the processor as you can, even though it is unfortunately yoked to slow things like RAM. And so you can see them. If you open good old Task Manager, I have 41 processors, which is 677 threads. So each process has many threads, and each thread has many handles. The handles are just pointers, essentially, to objects. If you open a file, you get a file handle. It's not a pointer simply, but it's a way to refer to it. So now when you close a file, you have fclose of fp telling it which file you're trying to close. Those are handles. They are named objects used by the processes and the threads. All right, and that's the game here. So you have a lot of handles. I don't know anybody that really cares about handles, except mutexes, which we'll talk about a little in the malware analysis class. Mutexes are used for inter-process communication. And there is a technique I heard about from the guest speaker that spoke here on Monday, which I'd never heard about before, and I cannot find any reference works for, where he says there is a way to inoculate your machine against ransomware. You just create all the mutexes that ransomware wants to create. See what happens, ransomware will come to your machine, someone double clicks on an attachment, and it looks for a mutex, which is an object in RAM, a handle created with a funny name. When the ransomware has already infected your machine, it puts that there, so it knows, don't reinfect this box, it's already infected. So somebody has a defense technique where you create mutexes for all the known ransomware, so it won't infect you because it thinks you're already infected. Which sounds pretty awesome, but I couldn't find any articles about it or any tool that does it.
That would persist across rebooting your machine?
Not unless you installed some kind of software that kept on putting them in there, but I think that's what there is. So some kind of product that will keep putting them back. It sounds pretty clever, but I don't know, I couldn't find more about it. Anyway, here's Process Explorer, and this will show you details of the threads. So in here, you're looking at, I think, application frame, Explorer.exe, which is the process that draws your desktop and the start button. And here are all the threads with thread IDs. And here's the amount of CPU they're getting, and something about how many cycles of CPU they've had, and the start address, and so on. So you can actually see all the little threads inside the process in case you want to. I'm not aware of any occasion where I would really want to do that. Look at the threads or the handles, but they are available. All right. So, what portion of the DIL lists the entry points it provides? All right, guess I'll quit it. 30. All right, those are the exports. And I ought to mention in passing, we are gonna do an exploit to get around a non-executable stack where you use existing code. So you have a routine where you jump into this address, it executes hundreds of instructions, gets to the end, and then returns. And instead of going to the recommended entry point, you jump like just 2 instructions before the return. So you get 2 machine language instructions from this routine, and then another routine, and you build your exploit with these little chunks of code, like making a letter by cutting words out of the newspaper and gluing them on. That's return-oriented programming, and it's very powerful, and Microsoft likes to pay people to fix these things. They paid someone 100 grand for finding the vulnerability, and they paid them another 100 grand for fixing the vulnerability, and the fix is amazingly simple. They added a feature to the DLLs that lists the right ways to come in, and you cannot run the DLL at any other address other than the official entry point. It's another one of these things that looks obvious once somebody thinks of it, but that's only in like the latest version of Windows, like 2016, or I think 2012 R2 with the Emmett toolkit or something. That ends a whole category of attacks that involve using unexpected pieces of code. Anyway, I mentioned it. So the exports are the right way to enter the DLL, but for most versions of Windows, there's nothing stopping you from entering it at a different address, although there should be.
So that would neutralize any like return-oriented attack
It's,
unless you use the currently running program's code.
well, I think it would, but of course, there's always some way around anything. There's probably some way to turn that feature off. And there's probably some code that doesn't have that feature turned on somewhere. So, nothing's ever perfect.
Right.
But it is a pretty good defense. Yeah. All right. So, which memory section is a single block in Linux, but many pieces in Windows? All right. Guess I can quit at 25. So that's the heap. There are many heaps in Windows. There are many complicated articles detailing all the different heaps. We're not going to go too deeply into it in this class. Okay, which one of these has the largest number of instances in Windows? All right, I'm quitting at 25. All right, and that's handles. Every process has many threads, and every thread has many handles. Handles, there are more of them than anything else. All right. And what's the allocation unit for CPU time? All right, I'll quit at 25. All right, and that is the thread. The whole point of threads is each thread can move forward separately, and therefore it's the thing that gets some CPU time. All right, now this I found very enlightening. This is why Windows is the way it is. Microsoft has never made any bones about the fact that they are a for-profit business and their purpose is to make money. And like Facebook, they had the sense to realize that the way to make money selling Windows is to make Windows useful for developers who want to make money. So they want not only to make it easy to sell Windows, they want to make it easy to sell software that runs on Windows. And they want to make it so easy that you can sell modules to people, like libraries and little things that they can reuse easily. So this is where you get the DCOM and the DCE-RPC, the Distributed Computing Environment, Remote Procedure Calls. This is a brilliant way to make money as long as you don't care about security. And that was Microsoft's official position until 2002, that security is a total waste of time. We are just here to put out features. More and more features and more exciting programs, that's what people want, and security is just a waste of time. So if you think that way, then you'll see what's cool here is if you want to build an application, you have an idea for a game or a new spreadsheet or whatever you want, rather than writing all the code, you just buy pieces of code from developers. I want a little routine that does this, a routine that does that, and then you just sort of patch them together. with a high-level language like Visual Basic, and by plugging in these modules like Lego, you built your program without really having to write much. So people should be able to write something and have it reused for a different purpose later easily. That's the goal here. So there were these COM objects. You can write your code as little objects, and then a calling routine will call this object and that object and that object. And so you write an independent thing, sort of like a library, this COM object that offers certain services, and you write this other file with interface description language that specifies what kind of inputs you expect and what kind of outputs it's going to put out. So here's an IDL file. Let me get this thing out of the way, if I can figure out somewhere it's out of the way, and if it will let me move. All right. So you have, I'll make you use this one because then I can use the pointer. They got UUID here, which is a universal ID, supposedly. Then you got a handle. Here's a structure defined with various types. Here's a long integer. Here's a unique string, and so on. Here's another long integer. So you define these data structures, which are the objects you feed in for input and the things that come out as output. And then you can write up documentation saying this routine does this function and sell it to people. So that's the IDL. It specifies how long the inputs and how long the outputs are. All right, so there are ways to load a COM object. You can load it directly into process space as a DIL. Then it's running in the RAM on the machine, and processes on that machine can request service from that COM, from the Service Control Manager. That's what the Microsoft services are that run in the background. If you do that, it's more stable and secure than putting it directly in one process, but it is slower. In-process calls are 1,000 times faster than calling something in a different process. So you slow things down by putting them in a shared library, but you make it easy to reuse code. But the genius of Microsoft is you can, well, here's it is running in services. It'll run in this services app, the Service Control Manager. The next thing is DCOM calls. You can take code. So think about what's happened here. You had a subroutine that was originally part of one program, where you just use it. Then you say, this is so useful, everyone else should use it too. So you put it in a service, it makes it 1,000 times slower, but now every application on the machine can access it. Now you say, this is really great, I want everyone to use it, so you connect it to the network card so things on other machines can call this routine. And that's what the DCOM does. So now you can call a COM interface on a different machine, which is again 10 times slower again. But what's happened here is very much like the migration to the cloud. Your developer originally wrote a subroutine to run inside one program. Then you took that and made it available to every program on the machine. Then you took it, made it available to everyone in the world over the internet. Probably the original developer never knew that was going to happen and didn't think about the security consequences. And this is very much like what happens now. You have a data center with your web server and your email server, and you have firewalls and intrusion detection systems, and then you make images and put them all in the cloud where every one of them is directly connected to the internet, and people don't know that. So you've taken things out of their nice, safe sandbox environment and exposed them to the whole world. But that's the point here. If you don't think about security at all and you just think about the best way to make money, that's what this is designed for. So here's how it works. This is what's listening on port 135. You probably heard this all through the time. 135, 137, 139, and 445 are Microsoft's remote procedure call and file sharing ports. You should always block them at the firewall, never let people at them because they're all full of security problems, and this is why. Those are services that were originally written to run in a nice contained sandbox and were just lifted and exposed to the world at this port. So you have an RPC Endpoint Mapper running on 135, and if you connect to it and watch it in Wireshark, you see information come here where it sends a map request and then it gets a map response. So many, many services are being offered out the same port. And if any one of them has a buffer overflow or a dangling pointer or any other vulnerability, you can get in the box, and many, many worms spread through these ports. So your map request shows you available functions, and then you get this floor, UUID, and here's another floor. These are the various services it's offering, and the UUIDs for them. And so many services are being offered by the machine over the network, and you can access them, and if any one of them has a vulnerability, you get in. So a lot of components depend on RPC. If you go into the services control panel and double-click remote procedure call, you'll see it depends on other things, the DCOM mapper and the RPC endpoint mapper. And there's a lot of things that do. And here's all the components that depend on this service: ActiveX installer and background intelligent transfer service, and many other functions depend on RPC. All right, so that's the point. You have code that was probably originally intended to run inside one app that is now suddenly shared with the whole world. So there are a whole bunch of security tools to scan and attempt to exploit these. Recon, and you can do recon to find them. You can do fuzz to find the vulnerabilities with Spike. Spike is supposedly the best tool for this. I didn't write a Spike project. It would be a pretty good thing to have in the class though, but I didn't get around to it when I developed this class, and I may add it this semester, I'm not sure. I think I looked at it and it was kind of complicated. Fuzzers tend to be pretty complicated. Dumb fuzzers don't find much. The smart fuzzers require a lot of customization of the data you're feeding in. So, tokens. A token defines your user rights. So if you remember, you can open a command prompt or you can open an administrator command prompt. The difference between those is the process is attached to a different token, and the token determines what it's allowed to do. Token is like an ID card. It's a 32-bit integer, and it's a pointer to a data structure, which then defines user rights. Now, the problem is there are many tokens available. You can see some of them there. Well, more of them are coming up here, I think. So I think these are the tokens. Oh yeah, here we are. Here's NT Authority System is this one, AAA. Here's other ones. Here's SAM. SAM is 555, and System is AAA. You can just read these values and you can just copy them from one process to another. So you can just elevate your process to a higher token. It's surprisingly poorly defended. And that's the game here. You can create a thread and you can copy an available token to it so you can make yourself system or administrator or any token that's available. And there are typically tokens available on a machine for any user who has recently authenticated because there's some process running that still has their token attached to it. All right. So that's one good bit of fun. Then there's exception handling. This is the way to get in a lot of Windows machines, so we'll be using this one, the structured exception handler. When you have an error, like an attempt to access memory outside the range available to your process, or attempt to run a kernel routine when you're not in kernel mode, but you're in user mode, or division by zero, or anything else that the processor cannot do, it raises an exception. It says stop executing code and go to the exception handler. Now the exception handler can be controlled by the application developer. You can capture exceptions and print custom error messages for your program, or you can not handle them, and then they'll go to the operating system, which will open something like Dr. Watson in the old versions, or some kind of debugger, or maybe the blue screen of death. So you have an opportunity to capture exceptions before the processor does, and that's the structured exception handler, which is just a list of pointers. This exception goes there, this exception goes there. Anything I didn't handle will now go back to the operating system and it will do whatever it wants to do. You can find it in Immunity Debugger. You can just view the SEH, and it's just a series of addresses and then handlers. So if a certain exception appears, it'll go here, another appears, it'll go there, pointing to somewhere in NTDIL. We are going to have several projects where you exploit this and you alter the contents of the SEH, which is a way to take over the machine. Corrupt the SEH, pointing to your injected code, and then trigger an exception with a divide by zero or something, and it's one way to make instructions go to the code you put in. All right, there's a lot of ways to do it. There are various places you can change a value that will take control of the machine. All right, and then there's debuggers, and this is how debuggers work. Their debuggers actually work by triggering exceptions after each instruction. That's how they can step through instructions and then capturing the code again. Anyway, Soft Ice was supposed to be very powerful but very hard to install, and I've never used it. OllyDbg is very popular. The Immunity debugger that came from it is the more modern version of it. Those are the main ones used by hackers and defenders alike. WinDebug is the one used by Microsoft. It is a very clunky text-only interface, hard to read, but it's the only one that can debug the kernel. Now, debugging the kernel you're going to do in this class. This used to be the hardest, most miserable project in the class, where every student was stuck and having to try again and again and sending me pitiful emails. And it got easier because the way this used to work is you would connect two machines with a serial cable with those 25-pin connectors, which don't even exist anymore. Then one machine was the master and one was the slave. You'd run the buggy code in the slave in kernel debug mode. You boot it in a special mode, and then this other machine can observe the kernel. So when this kernel has a problem, instead of showing the blue screen of death and dying, it communicates through the cable and lets this one see the error message. This is how you debug device drivers. Device drivers run in the kernel, and Microsoft found that I think 80% of all blue screens of death are caused by third-party device drivers. And they've felt pretty upset by this. I mean, here it's not their code. Everybody blames Microsoft for all these blue screens of death. Anyway, what happened is Mark Russinovich wrote a very powerful tool that we're going to use that makes it possible to do kernel debugging to some extent with just one machine, which is pretty awesome. And I don't remember if we're using this class or I think we're doing it. Might be mixing my classes up. Maybe we're not doing that. It's in the other class we're doing that. All right, anyway, 126 we're doing kernel debugging. Anyway, but that's the game. WinDebug can debug the kernel. It's just not much fun. OllyDbg was very nice and very popular. They upgraded it to 2 and they totally broke it. It will break your heart. It can't even find all the imports for a DIL anymore. Some of them are just missing. There's nothing more horrible than a program that lies to you about what's going on. So Immunity is what took over OllyDbg and kept it alive, and Immunity Debugger is the modern, fully living debugger based on it. Some people continue to use OllyDbg, the old version, which is probably fine for 32-bit code, but Immunity is more modern. And here's how it looks. When you open up a debugger, you are presented with far too much information, so it can be confusing. So you start with the main thing. This tells you what's going on. When you load a program in a debugger, the first thing you have to learn is it stops. It loads the program and then pauses. So if you're expecting to get anything done, you have to run it with the run button up there, that red button arrow going to the right. But when it loads, it breaks at the first instruction and it shows you that it's paused with this thing down here that I just can't find anywhere to put it that's not in the way. So you see that it's paused down there. Here's the basic components. You have assembly code here. You should recognize this stuff, move and or, and repd is a copying a whole block of instructions. Here's what Joe McCrae calls the Wireshark pane. This is just a hex dump of anything. You can dump various things there. Here's the stack. So it shows the values on the stack, and if it's a pointer to something, it tells you what it points to here. If it's pointing to a string, it'll show you the string. Here's something pointing to the structure section handler, and here's the good old registers, EAX, B, C, D. Here's the extended instruction pointer down here, set off a little bit, and some of the flags are set up there. So that shows you the condition of the processor. And when you run the program, all these things will flicker as it goes ahead. All right, and that's the joy of Immunity, and you'll be using it to develop Windows exploits. Just like you'll be using GDB to develop Linux exploits, you'll be using Immunity to develop Windows exploits. As you'd expect, it's got a GUI and it looks a lot prettier, but it's the same kind of information that GDB is showing you. All right, so let me get my iClickers listening, see if I can live with it up there, I don't know. And, all right, which file lists the inputs and outputs of an object? All right, I'm quitting at 30. All right, and that's IDL, which is something descriptor language, although I forget, is it input descriptor?
Interface.
What is it?
Interface.
Interface, thank you. Interface descriptor language, good, that's what it is. Good. All right, where's a 128-bit value? Same size as an IPv6 address. Quit at 25, I think the answers are in. That's that UUID, the identifier. Microsoft likes this UID structure. There's a thing called a GUID that refers to many objects, which they call a global unique identifier. And then the GUID for like control panel is the same on every machine. So it's not globally unique at all. But that's the general rule of thumb with all Microsoft things is whatever the name is, that's the opposite of what it is. Anyway, so if you divide by 0, what structure is used? You won't get the blue screen from divide by 0, because that's not a kernel flaw. It only gives the blue screen when you have crash in the kernel because it can't figure out what to do at all. If it's in user land, the heart of the operating system can survive and pop up something like Dr. Watson. But if it's in the kernel, it just gives up and dies. Says, I don't know what you're talking about. I'm not going to run anything anymore. That's the structured exception handler. That's an exception, but it's not a particularly serious exception. All right. All right. So which one listens on port 135? All right, I'll quit at 25. All right, that's RPC, the Endpoint Mapper. I must say, I've been teaching for like 15 years saying Microsoft RPC is the source of many security vulnerabilities, and I was very pleased to finally get more clue about why. It's a well-known fact, but I didn't understand why until I started reading this book. Anyway, all right, which one is 32-bit value? Clickers. I'm quitting at 25. All right, and that is the token that determines your user rights. And ever since Vista, accounts, normal standard accounts have two tokens, an elevated token with administrator privileges and a non-elevated token with normal user privileges, and you go from one to the other with user account control, switching the token of your process. All right. Which debugger can debug the kernel? Quit at 25. Only WinDbg, the one Microsoft uses, can do it. All right. These others are strictly user land, which is mostly what you want to do. Unless you're writing device drivers, you probably don't want to worry about the kernel. All right, which one had a good old version and a bad new version, which is kind of contrary to the way things usually go. Not a lot of people will break something and then call it the new version. Microsoft has done that. Windows ME was a beta version, and they decided to abandon it, and they said, well, let's just sell it the way it is. You've got to have a certain gall to do a thing like that. Anyway, I'll quit at 30. All right. So that is OllyDbg. OllyDbg 2 is junk. OllyDbg 1.1 is fine. All right, I'm going to stop the recording and see who won. This is 127, chapter 6, I think.